Tonight, we are going to talk about something that most science channels get completely wrong. Not slightly wrong, fundamentally, embarrassingly wrong. You've seen the movies, you've seen the TV shows. Astronaut loses their helmet, floats serenely for a few seconds, gets rescued, walks it off. Or the other extreme. They explode like a balloon, freeze solid in 2 seconds, shatter into pieces. Neither of those things is true, and the actual reality is somehow more disturbing than both versions combined. So, here is the question we're starting with. If you were suddenly exposed to open space right now, no suit, no ship, just you and the void, what would actually happen, and how long would it take?
The answer involves biology, physics, chemistry, and a pressure difference so extreme that your blood starts doing something it was never supposed to do. We are going to work through this carefully, layer by layer, because understanding what deep space actually is requires understanding what your body actually needs and how completely space refuses to provide any of it. What your body silently assumes every second of your life. Right now, without thinking about it, your body is operating inside a very specific set of conditions. Atmospheric pressure of roughly 14.7 pounds per square inch is pressing in on you from every direction. About 21% of the air around you is oxygen. The temperature is somewhere between freezing and boiling. Gravity is holding your blood in roughly the right places. A magnetic field the size of a planet is deflecting charged particles away from you. A layer of ozone 40 kilometers above your head is blocking wavelengths of ultraviolet light that would otherwise shred your DNA.
None of this requires any effort on your part. Earth provides all of it automatically, continuously, for free. Now here is the thing that most people never stop to consider. Your biology was shaped by these conditions over hundreds of millions of years. Every biochemical process in your body, every enzyme, every cell membrane, every blood vessel and lung and nerve fiber, all of it was calibrated to work at 1 atmosphere of pressure, in the presence of oxygen, within a narrow temperature window, shielded from radiation. Your body does not just prefer these conditions, it literally cannot function without them. Deep space removes them all, simultaneously, instantly. Let us start with the one that kills you fastest. The pressure problem, and why it is stranger than you think. Here is a comparison that might help. Imagine a bottle of carbonated water. When the bottle is sealed, the carbon dioxide stays dissolved in the liquid. The pressure inside the bottle keeps the gas in solution. The moment you open the cap, pressure drops and gas bubbles form throughout the liquid in an instant. That hissing, fizzing release is carbon dioxide coming out of solution because it no longer has to stay there. Your blood is doing something similar right now, in reverse. At normal atmospheric pressure, gases, including nitrogen, oxygen, and carbon dioxide, stay dissolved in your blood and tissues. The pressure keeps them there, the same way a sealed bottle keeps the fizz in. What happens when you open that bottle at sea level? Gradual bubbling. What happens when you take that same bottle and suddenly drop the pressure to essentially zero? The contents erupt. That is what vacuum does to human blood. The dissolved gases do not gradually come out of solution, they explode out. Bubbles form everywhere simultaneously, in your veins, in your arteries, in the fluid around your joints, in the fluid behind your eyes, in the tissues of your brain. Scuba divers can experience a mild, slow version of this if they ascend from depth too quickly. It is called decompression sickness, and even the mild version is agonizing. Joint pain so severe it makes people bend double, which is how it got the nickname the bends. The version caused by instant total vacuum is not comparable in any meaningful way. And this is only the beginning of what pressure loss does. What happens to water in a vacuum, and why your body is mostly water? Here is a physics fact that sounds impossible until you think it through. Water boils at a temperature that depends on the surrounding pressure. At sea level, you need to heat water to 100 degrees Celsius to make it boil. At the top of Mount Everest, where atmospheric pressure is roughly 1/3 of sea level, water boils at about 68 degrees Celsius. That is why you cannot make proper tea at altitude. The water is technically boiling, but not hot enough to extract flavor correctly. Follow that logic to its conclusion. Keep dropping the pressure. As pressure falls toward zero, the boiling point of water falls with it. In a near-perfect vacuum, water boils at body temperature, 37 degrees Celsius, the same temperature your body maintains right now. What does this mean in practice? Your moisture on the surface of your eyes boils away. The saliva on your tongue boils. The moisture coating the inside of your lungs boils. Not because you are hot, because the pressure that was keeping those liquids liquid is gone. This has actually been observed in controlled experiments with vacuum chambers. Water at room temperature placed in a vacuum does not wait to be heated. It flash boils almost immediately. The physics is settled and well understood. And since your body is approximately 60% water by mass, you can draw your own conclusions about what this means for extended vacuum exposure. One documented case from 1965 at the Johnson Space Center involved a technician whose suit failed during a vacuum chamber test. He was exposed to near-vacuum conditions for approximately 14 seconds before the chamber could be repressurized. He described, after regaining consciousness, the sensation of his saliva on his tongue boiling. That is the last coherent sensory memory he had before losing consciousness. 14 seconds. He survived only because he was immediately repressurized and given medical attention. In actual deep space, there is no repressurization, there is no chamber, there is no rescue arriving in 14 seconds. The oxygen question, and a number that might surprise you. Your brain makes up about 2% of your body mass. It consumes about 20% of your total oxygen supply. That ratio tells you something important. The brain is extraordinarily expensive to run, and it is extraordinarily sensitive to interruptions in fuel delivery.
In normal circumstances, if you hold your breath, you have roughly 1 minute before you lose consciousness, and that is with your lungs full of air and your blood still carrying oxygen. Cut off the oxygen supply completely, no air in the lungs, blood that is increasingly compromised by gas bubbles and cannot carry oxygen effectively, and the timeline compresses sharply. Consciousness fades in approximately 10 to 15 seconds, not because of pain or trauma, simply because the oxygen already in your bloodstream gets consumed by your brain, and nothing is replacing it. The brain dims like a phone with a battery at 0%. Vision narrows first, then sound fades, then nothing. This is worth sitting with for a moment because it is actually one of the least agonizing aspects of vacuum exposure. You lose consciousness before most of the other damage has time to become something you register as suffering. The 14-second timeline is not just a curiosity, it is roughly the window you have before your brain shuts down. Brain damage begins within minutes of oxygen deprivation. Irreversible brain damage begins within 4 to 6 minutes. Clinical death follows.
But here is something interesting. None of the other problems care whether you are conscious or not. They keep developing regardless. Let us talk about what the body looks like from the outside during vacuum exposure, because this is where the movie version gets replaced by something genuinely strange. The swelling and what it tells us about internal pressure. Your skin is not just a passive covering. It is a flexible membrane that responds to internal pressure. Under normal conditions, the pressure inside your body and the pressure outside your body are roughly equal. That balance is why you don't feel the atmosphere pressing down on you. Your tissues push back with equal force. Remove the external pressure, and the internal pressure has nothing to push against. Gas trapped in tissues, expanding gases coming out of solution, the low-level pressure your cardiovascular system constantly maintains, all of it starts pushing outward with nothing to resist it. The result is swelling, rapid, pronounced, visible swelling across the entire body. This is not like the swelling you get from a sprained ankle. This is systemic. Tissue throughout the body expands as internal gases have no external pressure to contain them. The body roughly doubles in apparent volume. Clothing would tighten and eventually tear. Joints would feel as though they were being inflated. The face would become unrecognizable within seconds.
Think of a sealed bag of chips that you bring on a plane. At altitude, where cabin pressure is lower than sea level, the bag puffs up. The pressure inside the bag, which was balanced at sea level, is now higher than the pressure outside. The bag expands. Your body, in vacuum, is the bag, except the bag has no rigid walls to stop the expansion. What limits human swelling is the skin and connective tissue, which are elastic but not infinitely so. The swelling stops short of literal explosion. That particular movie trope is false, but the swelling that does occur causes damage to blood vessels, disrupts circulation, and contributes to the cascade of systems that are all failing simultaneously. A timeline built from physics and documented evidence. Let us walk through the first 2 minutes second by second, not for drama, but because the specific sequence reveals something important about what actually kills you and in what order. 0 seconds. You are exposed to vacuum. Pressure drops from 14.7 pounds per square inch to essentially zero. The drop is instantaneous. Within 1 second, gas in your lungs begins expanding. If you are holding a breath, lung tissue starts tearing as the trapped air tries to expand to fill infinite space. If you exhaled, which is the correct instinct, air rushes out. Simultaneously, moisture on your eyes and tongue begins to boil away. Within 2 to 3 seconds, dissolved gases start forming bubbles throughout your blood and tissues. The process is called ebullition. Skin begins to swell.
Within 6 seconds, circulation becomes increasingly compromised. Blood carrying gas bubbles does not flow normally. Your heart is still pumping. The heart is remarkably resilient, but it is pushing increasingly compromised fluid through vessels that are being damaged by bubbles. Within 10 to 15 seconds, oxygen levels in the brain fall below the threshold needed to maintain consciousness. Vision narrows to a point. Hearing fades. You lose consciousness. At 30 seconds, severe swelling is visible throughout the body. Blood pressure is erratic. The heart continues trying to do its job, but the fluid it is moving is increasingly foam-like. At 60 seconds, even if you were somehow rescued and immediately repressurized at this point, neurological damage would be severe. The window for full recovery closed at roughly the 15-second mark. At 90 seconds, cardiac function is failing. The heart may still be beating, but weakly and irregularly. At 2 minutes, clinical death by any standard measure. This is the actual timeline, not the movie timeline, not the frozen in 10 seconds version, not the peaceful floating until the air runs out. 2 minutes from exposure to death, and most of that time you are unconscious.
So, if space is a vacuum, what about the International Space Station? Here is a question worth answering directly. The ISS is in space. How is it different from deep space? The station orbits at about 400 kilometers above Earth's surface. At that altitude, the atmosphere is so thin that for all practical purposes it is a vacuum, roughly 1/trillionth of sea level pressure. Exposure to the environment outside the station would produce exactly the timeline we just described. But the station is inside Earth's magnetic field, which changes one crucial thing: radiation. Earth's magnetic field extends far beyond the atmosphere, deflecting charged particles from the Sun and deflecting a significant fraction of galactic cosmic rays. The ISS sits within this protective bubble. Not completely. Radiation levels aboard the station are roughly 150 to 200 times higher than on Earth's surface. But the bubble provides meaningful protection compared to deep space beyond it.
The second difference is distance. The station is about 400 kilometers up. A Soyuz spacecraft can return a crew to Earth in under 3.5 hours. In an emergency, rescue is a realistic option. That changes the psychological equation for astronauts and the practical equation for mission planners. Deep space, meaning beyond Earth's magnetic field, removes both of those advantages. Full radiation exposure, no practical rescue. Those two differences turn a dangerous environment into one that operates on a completely different threat level. The radiation reality, and why this one is harder to see.
Vacuum kills in seconds. Radiation kills over weeks, months, or years. That difference in timescale makes radiation feel less urgent than it is. Here is a useful comparison. Imagine you are standing in a field during a thunderstorm. Lightning could strike you. That is an acute, immediate threat. But imagine also that you are standing in a field that has been contaminated with radioactive material. You cannot see it, feel it, or smell it. Every hour in that field adds to a cumulative damage total that your body is silently keeping track of and will eventually present to you as a cancer diagnosis 15 years from now.
Deep space is the second field, except the contamination is not radioactive soil, it is the universe itself. Space is filled with radiation from multiple sources. Solar radiation includes the full electromagnetic spectrum, from radio waves on the gentle end to X-rays and gamma rays on the energetic end. Earth's atmosphere filters out most of the dangerous high-energy portion. In space, it arrives unfiltered. Solar particle events are separate from this baseline. During solar flares and coronal mass ejections, the Sun releases bursts of charged particles, protons and heavier ions, moving at significant fractions of the speed of light. A major solar particle event can deliver radiation doses sufficient to cause acute radiation sickness within hours. Earth's magnetic field deflects these particles toward the poles, where they create auroras. In space beyond the magnetic field, they hit directly. But the most persistent and, in some ways, most insidious radiation threat comes from outside the solar system entirely. Galactic cosmic rays, the universe's background noise. Galactic cosmic rays are atomic nuclei, atoms stripped of their electrons, accelerated to enormous speeds by the most violent events in the universe: supernova explosions, neutron star collisions, material falling into black holes. These events release energy on scales that are difficult to comprehend, and some of that energy goes into accelerating individual particles to speeds approaching the speed of light. A single galactic cosmic ray particle can have more energy than a baseball thrown at professional pitching speed, concentrated into a single atomic nucleus. It has been traveling through the galaxy for millions of years. It has crossed light years of empty space, and when it hits biological tissue, it does not politely stop at the outer layer. It travels through you, ionizing atoms along its path, breaking molecular bonds, occasionally shattering a DNA molecule or destroying the machinery of a cell entirely. One cosmic ray hit will not end you. You are hit by cosmic rays even on Earth. A few per square centimeter per second make it through the atmosphere and magnetic field. Your DNA repair mechanisms handle most of the damage. The fraction that causes cancer or other lasting effects is a minor risk factor, not a major concern. In space beyond Earth's magnetic field, the flux is orders of magnitude higher, hundreds or thousands of particles per square centimeter per second, depending on location and solar activity. Each has a small probability of causing lasting damage. More particles means higher probability. Over months and years, the cumulative damage adds up to something that cannot be ignored. Astronauts on the ISS, again partially protected by Earth's magnetic field, receive radiation doses about 100 or 200 times higher than people on the ground. A 6-month stay on the station increases lifetime cancer risk by roughly 1%. That sounds small, but consider you are adding 1% to whatever your baseline risk already is. For someone who might live another 50 years, that is meaningful. The Mars number and what it actually means. NASA has run the calculations for a round trip to Mars. Under current technology and current spacecraft shielding capabilities, a crew would be exposed to radiation during the roughly 18-month to 2-year total mission duration that increases lifetime cancer risk by approximately 5%. 5% added cancer risk is, by the standards of regulated industries on Earth, quite high. It exceeds the limits set for radiation workers in most countries. It is considered on the outer edge of acceptable for trained volunteers who fully understand what they are accepting. It is emphatically not safe in any ordinary sense of the word. And Mars is close as these things go. It is our nearest planetary neighbor. A mission to the moons of Jupiter, which would be the logical next step for outer solar system exploration, would take years. The radiation exposure scales with time in deep space. Longer mission, higher cumulative dose, higher cancer risk, and potentially other effects that we are still studying. There is emerging evidence that cosmic ray exposure affects the brain in ways beyond cancer risk. Animal studies exposing subjects to simulated cosmic ray conditions have shown measurable changes in brain structure and behavior, memory impairment, reduced cognitive flexibility, increased anxiety-like responses. Whether these translate directly to human experience in space is still being investigated, but the biological mechanism is plausible. Cosmic rays can reach brain tissue as easily as any other tissue. For a crew on a multi-year mission, cognitive decline is not just a personal health concern, it is a mission safety issue. People making critical decisions in a crisis need their full cognitive capacity. Any degradation in that capacity is a direct threat to mission success. Why shielding does not solve this the way you might expect? The intuitive solution to radiation is shielding. Thick walls, lead lining, layers of material to block particles. This works reasonably well for some types of radiation, but galactic cosmic rays present a specific problem that makes simple shielding less effective than you would hope. When a high-energy cosmic ray hits a dense material like aluminum, it does not just stop. It shatters nuclei in the shielding material, producing a cascade of secondary particles that spread out in a cone. In some cases, this secondary shower actually delivers more total radiation dose to anything behind the shield than the original particle would have delivered on its own. Heavier shielding, counterintuitively, can make things worse. The materials that work best as radiation shielding for cosmic rays are hydrogen-rich materials, water, polyethylene, foods high in hydrogen content. Water is actually quite effective because hydrogen absorbs energy from cosmic rays without producing as many secondary particles.
But to significantly reduce cosmic ray dose, you need meters of water surrounding the crew compartment. Meters of water in all directions. That is thousands of kilograms of shielding mass. Every kilogram of mass you want in space has to be launched from Earth, and the economics of launching mass to space are brutal. Current launch costs run from thousands to tens of thousands of dollars per kilogram, depending on the vehicle and destination. Even at the lower end of that range, the cost of enough water shielding for a Mars transit craft would be in the billions of dollars for the shielding alone. Spacecraft designers make pragmatic trade-offs. Current spacecraft have thin aluminum hulls, a few millimeters thick. They provide minimal radiation protection. They are chosen because mass is the enemy of spaceflight, not because they are adequate protection. Future spacecraft may carry more shielding, perhaps water tanks arranged around the crew habitat or specialized polyethylene panels, but eliminating cosmic ray exposure entirely with passive shielding is not currently achievable. The result is that any human crew spending extended time in deep space will accumulate radiation dose. The question is not whether it happens, but how much and what the long-term consequences are. This is a known, accepted compromise in current mission planning. It is also a fundamental limit that we have not yet engineered our way around. Temperature in space, and why the answer is counterintuitive. Here is a question. If space is extremely cold, why do spacecraft overheat? The answer reveals something fundamental about how heat moves and does not move in a vacuum. On Earth, you lose body heat through three mechanisms. Conduction is direct contact. Touch a cold surface, and heat flows from your warmer body into the cooler surface. Convection is movement of fluid. Air warmed by your body rises, cooler air replaces it, and the continuous circulation carries heat away. This is why wind makes cold weather feel colder. It accelerates convective heat loss. Radiation is emission of infrared light. Every object above absolute zero emits electromagnetic radiation, and objects lose heat through this emission, constantly. In a vacuum, conduction does not work because there is nothing to conduct heat into. Convection does not work because there is no fluid to carry heat away. Only radiation remains. This changes everything. An astronaut floating in space loses heat only by radiating infrared light, and radiation for an object at human body temperature is a relatively slow process. You would cool down, but over hours, not seconds. The dramatic frozen solid in moments scenario from movies is physically impossible without a medium to conduct heat away rapidly. The actual thermal threat in space is often the opposite. Electronics generate heat. Human bodies generate heat, roughly 100 watts while resting, more during activity. In a sealed, insulated spacecraft with no convection to distribute that heat, temperatures rise quickly. The ISS has radiator panels the size of tennis courts extending from its structure. Their function is to radiate waste heat into space. If those radiators fail, the station overheats. This nearly happened in 2013 when an ammonia leak threatened the cooling system. Emergency spacewalks were required to repair it. Sunlight adds another layer of complexity. Near Earth, sunlight delivers roughly 1,360 watts per square meter to any surface perpendicular to the Sun. An astronaut in an EVA suit with one side facing the Sun and one side facing shadowed space experiences a temperature difference between those two sides that can exceed 300 degrees Celsius. The sunlit surface of a spacesuit can reach 120 degrees Celsius. The shadowed surface simultaneously approaches -100. Managing this gradient is a primary engineering challenge for spacesuit design.
What a spacesuit actually is, and what it costs. Most people think of a spacesuit as a very fancy jacket, something protective, something insulating, something that keeps air in. The reality is that a spacesuit is a miniature spacecraft. Every system that a spacecraft needs to keep its crew alive, a spacesuit needs to provide as well, except in a form that fits on a human body and allows movement. Pressure. The suit maintains internal pressure at roughly 4.3 pounds per square inch, lower than Earth's atmospheric pressure, but high enough to prevent ebullition and supply adequate oxygen. The lower pressure makes the suit less rigid and easier to move in. A suit at full atmospheric pressure would be nearly impossible to articulate. Oxygen supply. The suit continuously provides pure oxygen at a partial pressure sufficient for breathing. Using pure oxygen rather than mixed gas allows the lower total pressure. You need the right partial pressure of oxygen, not any particular total pressure. But pure oxygen is extraordinarily flammable. This is why the Apollo 1 fire in January 1967 was so catastrophic. 3 astronauts were conducting a ground test inside a cabin pressurized with pure oxygen at approximately 16 pounds per square inch, higher than atmospheric pressure. A spark from faulty wiring ignited cabin materials. In the oxygen-rich environment, the fire spread faster than any fire behavior training had prepared the crew for. The hatch could not be opened quickly enough. Virgil Grissom, Edward White, and Roger Chaffee died within seconds. Every pure oxygen system used in space since then reflects the lessons learned that day. Carbon dioxide removal. The oxygen you breathe is converted to carbon dioxide as your body metabolizes it. Without removal, CO2 builds up in the suit's atmosphere and becomes toxic within minutes. Current suits use lithium hydroxide canisters that chemically absorb CO2. The reaction is simple. Lithium hydroxide combines with CO2 to produce lithium carbonate and water. The problem is that canisters have a finite capacity. A standard spacewalk lasts 6 to 8 hours. The suit carries enough canister capacity for that duration plus margin. If a spacewalk runs significantly over time, the margin disappears. Astronauts operating close to their CO2 scrubbing limit experience dizziness, confusion, and shortness of breath, classic symptoms of CO2 buildup. This has come close to being a serious problem during extended spacewalks, and it drives the strict time limits that mission controllers enforce. Thermal regulation.
Your body generates heat continuously. A sealed suit traps that heat with nowhere to go. Modern suits use a liquid cooling garment, essentially a set of close-fitting undergarments with small diameter tubes woven throughout. Chilled water circulates through the tubes, absorbing metabolic heat from your skin. The water carries that heat to a backpack unit, where it is radiated away into space. If the cooling system fails, the astronaut has roughly 10 to 15 minutes before heat buildup becomes medically dangerous. There have been cooling system malfunctions during spacewalks. They are taken seriously. Mobility. A pressurized suit wants to be a sphere. That is the shape that minimizes stress on the pressurized fabric, like a balloon which always wants to be round. A spherical suit is useless for doing work. The engineering challenge is allowing joints to bend while maintaining the pressure seal. Every joint in a suit, shoulder, elbow, wrist, hip, knee, ankle, is a complex bearing or fabric accordion designed to allow articulation against internal pressure. Think of trying to bend a partially inflated bicycle tire. That resistance is what every movement in a suit fights against. After 6 hours of sustained work, the physical exhaustion is comparable to a full day of manual labor. Gloves are the most challenging component. Hands require fine motor control, turning bolts, handling tools, manipulating small components. Pressurized gloves resist every movement. Gripping an object requires squeezing against the pressure, trying to push your fingers open. After hours of this, hand muscles cramp and finger tendons ache. A documented occupational hazard among spacewalking astronauts is fingernail delamination. The nail separates from the nail bed over time due to repeated pressure cycling inside the glove. Painful, inconvenient, and a reminder that the body was not designed to operate inside pressurized rubber. The current NASA EVA suits, the Extravehicular Mobility Unit, or EMU, were designed in the 1980s. They have been refurbished, upgraded, and maintained, but the basic architecture is 4 decades old. Each suit cost several $100 million when total development and support costs are included. They weigh roughly 127 kilograms on Earth. In zero gravity, weight is irrelevant, but mass and inertia are not. A 127-kilogram object in motion wants to keep moving. Stopping it requires force. Working with that mass attached to your body adds to the physical demands of a spacewalk. The life support question at spacecraft scale. A spacesuit is life support for one person for 8 hours. A spacecraft is life support for multiple people for months or years. The engineering scales, but the fundamental constraints do not disappear, they compound. The ISS life support system recycles approximately 90% of the water aboard. Urine, sweat, moisture exhaled in breathing, condensation from humidity, all of it is collected, filtered, and purified. The purification process involves a distillation unit, catalytic oxidation, and ion exchange, producing water cleaner by most measures than municipal tap water. This is not luxury. Water mass is roughly 1 kilogram per liter, and launching mass to orbit currently costs thousands of dollars per kilogram. Recycling water already in orbit is economically mandatory for any long-duration mission. Oxygen is extracted from water through electrolysis. An electric current splits water molecules into hydrogen and oxygen. The oxygen is fed into the cabin atmosphere. The hydrogen is either vented or reacted with collected CO2 through the Sabatier reaction, named for the French chemist Paul Sabatier, to produce methane and water. The methane is vented, the water is returned to the recycling loop. The result is an almost closed system for oxygen generation, with resupply missions providing makeup for inefficiencies. Almost closed is the key phrase. No system is perfectly efficient. Filters clog, pumps degrade, seals develop tiny leaks, sensors drift out of calibration. On the ISS, resupply missions arrive several times a year, bringing spare parts, replacement components, and top-up supplies of consumables that the recycling systems lose to inefficiency. The station also has the benefit of being close enough to Earth that a crew can return in hours if a system failure makes the station uninhabitable. A Mars mission has neither of these safety nets. The journey takes 6 to 9 months each way, and the surface stay adds another roughly 18 months. Total mission duration is approximately 2 to 3 years. During that entire time, no resupply is possible, no rescue is realistic. If a critical system fails and the crew cannot repair it, the mission ends. Possibly the crew does too. The rocket equation and why mass is the enemy of everything. Here is a question that mission planners spend years wrestling with. Why do spacecraft have such thin walls? One answer is radiation. Thin walls are transparent to cosmic rays whether you want them to be or not. But the deeper answer is mass. Every kilogram of spacecraft that you want in orbit or on a trajectory to Mars has to be launched from Earth's surface. And the physics of launching mass is punishing. The energy required to lift 1 kilogram to orbital velocity, not just to altitude but to the speed needed to stay in orbit, is roughly 32 megajoules. That energy has to come from fuel, and carrying fuel adds mass, and that added mass requires more fuel to lift, which adds more mass in a compounding spiral that engineers call the Tsiolkovsky rocket equation. The result is that for a typical rocket, the payload that reaches orbit is roughly 2 to 5% of the total launch mass. The remaining 95 to 98% is fuel and structure discarded along the way. A Saturn V, the largest ever flown, the one that sent Apollo missions to the Moon, weighed approximately 2,800,000 kilograms at launch. Its payload to low Earth orbit was about 130,000 kilograms. That is about 4.6% payload fraction. What this means in practice is that every kilogram of shielding, food, water, spare parts, and life support equipment you want on a Mars mission costs a disproportionate amount in total launch mass, fuel, and ultimately money. Mission designers do not make spacecraft walls thin because they prefer thin walls. They make them thin because every additional millimeter of wall thickness adds kilograms that cost millions of dollars to launch and require additional fuel that adds more mass that requires more fuel.
The ISS has walls roughly 3 millimeters thick in most areas. That is about the thickness of a few stacked credit cards between the crew and the vacuum of space. 3 millimeters of aluminum. Debris, the problem that gets worse over time. At orbital velocity, roughly 7.7 kilometers per second for low Earth orbit, a paint flake has more kinetic energy than a pistol bullet. Kinetic energy scales with velocity squared. An object traveling 7 times faster than a rifle bullet has roughly 50 times the kinetic energy per unit mass. A paint flake 1 centimeter across, traveling at orbital velocity, can chip windows and puncture thin metal.
The ISS has been hit by debris thousands of times. Most impacts are too small to track or detect in advance. They leave microscopic craters and pits on the exterior surfaces. So far, none has caused a serious breach, but the station maneuvers to avoid tracked debris objects several times per year. Any object larger than about 10 centimeters can be tracked by radar. Anything smaller cannot be reliably tracked, but objects between 1 centimeter and 10 centimeters are still large enough to cause serious damage, and there are estimated to be hundreds of thousands of them in various orbital altitudes. The Whipple shield, developed by astrophysicist Fred Whipple in the 1940s, addresses this partially. The design uses multiple spaced layers of material. An incoming projectile hits the outer layer and shatters into fragments. Those fragments then spread out and hit subsequent layers with reduced energy per fragment. Multiple layers of distributed impacts rather than one concentrated one. This works well against small, high-velocity particles. It does not work against objects large enough that the energy is simply too great for any practical shield thickness.
For deep space missions beyond Earth orbit, debris is much less of an issue. The density of artificial objects drops dramatically beyond low Earth orbit. But natural objects, micrometeorites, dust particles from comets, the occasional small asteroid, are present throughout the solar system. In the outer solar system, the density of natural debris is lower. In the asteroid belt between Mars and Jupiter, it is higher. Any spacecraft traveling to Jupiter or beyond passes through that region. Zero gravity, the slow problem that creeps up on you. Here is one more threat that does not kill you in minutes, but changes you in ways that are still being understood. Zero gravity is not neutral for human biology. It is actively adverse, in ways that become clear after weeks and months rather than immediately. Bone density loss begins within days of entering microgravity. Your skeleton maintains itself partly through mechanical stress. The loads imposed by gravity and movement signal bone-building cells to remain active. In weightlessness, those signals disappear. Bone-resorbing cells continue working, but bone-building cells reduce activity. The net result is a loss of bone mineral density at roughly 1 to 2% per month in the most affected regions: spine, hip, legs. After 6 months on the ISS, astronauts have lost bone equivalent to several years of osteoporosis progression on Earth.
Recovery is possible. Bones mostly regain density over months after return to normal gravity, but the process takes longer than the loss.
and there are concerns about long-term structural integrity after repeated exposure or exposure at young ages during development. Muscle mass follows a similar pattern. Without the constant low-level effort of standing against gravity and carrying your own weight through daily activities, muscles atrophy. ISS astronauts exercise 2 hours per day, 7 days a week, specifically to minimize this loss. Even so, they return from 6-month missions measurably weaker and require months of rehabilitation. Vision changes have emerged as an unexpected and concerning finding. A significant fraction of ISS astronauts on long-duration missions have developed changes in visual acuity and eye structure, flattening of the eyeball, changes in the optic nerve, shifts in fluid pressure within the eye. The cause appears to be the redistribution of body fluids in weightlessness. On Earth, gravity keeps fluids preferentially in the lower body. In zero gravity, fluids shift toward the head and chest. Prolonged elevation of intracranial pressure appears to compress the back of the eye and optic nerve over time.
For shorter missions, this is manageable. For years in space, it is a serious concern. Some affected astronauts have experienced lasting changes in vision that did not fully resolve after return to Earth. The psychological dimension, the one that gets least attention. If you asked most people what the biggest challenge of a Mars mission would be, they would probably say radiation, or propulsion, or life support. Fewer would say psychology. But ask the people who study long-duration spaceflight, and psychology consistently comes up as one of the most significant unknowns. Here is a useful comparison. The most isolation-intensive Earth environment that has been studied systematically is Antarctic winter rover stations. A small group of people, typically fewer than 20, spend roughly 8 months isolated in an extreme environment with no possibility of evacuation during winter. The psychological effects are well documented. Social tension within the group, depression, cognitive slowing called the winter rover syndrome, difficulty maintaining motivation as the mission extends, sleep disturbances. And this is with the knowledge that winter ends, with communication to the outside world in near real time, with the sun eventually returning. A Mars mission is more isolating by every measure. Communication with Earth is delayed by minutes in each direction, up to 22 minutes one way at maximum separation, giving a round-trip communication time of over 40 minutes. You cannot have a conversation. You exchange messages that arrive like letters, not phone calls. Family and friends become voices of the past, not presences in the present. Earth itself disappears. The psychological effect of watching your home planet shrink to a point of light, then become indistinguishable from other stars, this has never been tested at the scale of a multi-year mission. Astronauts on the ISS can see Earth filling a significant portion of their visual field. The planet is present, enormous, continuously visible. On a Mars transit trajectory, that relationship inverts. Earth is a dim moving point. Mars is where you are going. Studies of analog environments, isolated habitats designed to simulate Mars mission conditions, including the HIC's missions in Hawaii and the Mars 500 simulation in Moscow, have shown that crew dynamics,
interpersonal conflict, motivation management, and sleep disruption become significant issues even in simulations with the knowledge that a short drive ends the experiment. The Apollo 13 lesson and what it means for deeper missions. In April 1970, Apollo 13 was 56 hours into its journey to the Moon when an oxygen tank in the service module exploded. The explosion was caused by damaged insulation on electrical wiring inside the tank, which created a fire which ruptured the tank. 2 of the 3 fuel cells that powered the command module were disabled. Oxygen for the cabin atmosphere vented into space. The service module was effectively dead.
The crew, James Lovell, Jack Swigert, and Fred Hayes, had approximately 15 minutes of power remaining in the command module. They used that time to power down non-essential systems and move to the lunar module, designed as a 2-person landing craft for roughly 2 days of surface operations, not a 3-person lifeboat for 4 days of emergency transit. What followed was a demonstration of human problem-solving under genuine existential pressure. Mission controllers and the crew identified that CO2 scrubbing capacity would be exhausted before they reached Earth. The lunar module used round lithium hydroxide canisters. The command module used square ones. Neither fit the other's housing. Using plastic bags, cardboard, tape, and hoses improvised from whatever was available, they constructed an adapter that made square canisters work in round housings. It worked. The crew survived. The reason Apollo 13 matters for deep space planning is this. It was a crisis that became survivable because the distance involved was small enough that improvised solutions had time to work. Light-speed communication between Earth and Moon introduces a roughly 2.5-second delay, negligible. Mission controllers and the crew were working in effective real time. The solutions developed on the ground could be implemented in space within minutes of being devised.
At Mars, that communication delay is between 3 and 22 minutes one way. A two-way exchange takes 6 to 44 minutes minimum. An Apollo 13 equivalent emergency on a Mars mission would require the crew to solve their own problems in real time without the ability to get meaningful input from Earth until the crisis might already be resolved or fatal. The hundreds of engineers who saved Apollo 13 would be watching a recording of a problem that was already over by the time their proposed solutions arrived. This is the central challenge that deepens every other challenge of a Mars mission. The crew is alone in a way that has no historical parallel in human spaceflight. The Mars environment. What waits at the destination? Let us say a crew survives the transit. They reach Mars. What do they arrive at? Mars has an atmosphere. That sounds promising. It is composed of roughly 95% carbon dioxide, 2.5% nitrogen, and small amounts of other gases. Total atmospheric pressure at the surface is roughly 0.6% of Earth's sea level pressure. That is thin enough that it is functionally vacuum for most biological purposes. You cannot breathe it, and the pressure it provides is insufficient to prevent ebulism in exposed human tissue. It does provide some protection against micrometeoroids and some attenuation of ultraviolet light, but these benefits are marginal.
Surface temperature on Mars averages roughly -60 degrees Celsius, with swings from about 20 degrees Celsius at the equator during summer days to minus 125 at the poles in winter. Liquid water cannot persist on the surface. The combination of low pressure and low temperature means water either evaporates or freezes immediately. There is water ice at the poles and underground. Accessing it requires drilling and melting equipment. Mars has no global magnetic field. It had one billions of years ago. Evidence of ancient magnetized rocks exists, but the core cooled and the dynamo stopped. Without a magnetic field, the solar wind has been gradually stripping away Mars's atmosphere for billions of years. The thin atmosphere that remains is the remnant of what was likely once a much thicker one. Today, surface radiation on Mars is approximately 250 times higher than Earth's surface radiation. Underground habitats covered by meters of regolith would be necessary for long-term habitation. The dust is fine, electrostatically charged and pervasive. Mars experiences regional and occasionally global dust storms that can reduce sunlight to a small fraction of normal for months at a time. In the 2018 global dust storm, NASA's Opportunity rover, which used solar panels for power, lost communication as dust coated its panels and reduced power output to zero. Any Mars habitat relying on solar power would need either large battery storage, nuclear power backup, or the ability to survive months with dramatically reduced solar input.
What self-sufficiency would actually require? Establishing a permanent human presence on Mars is discussed in popular culture as though it is primarily a transportation problem. Get people there and things work themselves out. The actual challenge is more fundamental. A genuine colony, one capable of surviving indefinitely without regular resupply from Earth, would need to produce its own food, generate its own power, manufacture its own spare parts, maintain its own social cohesion across generations. Each of these is a substantial engineering and organizational challenge on its own. Together, they constitute something more complex than any single human civilization has managed under much more favorable conditions. Food production in Martian regolith, the loose surface material, is not straightforward. Martian soil lacks organic matter, beneficial soil microbes, and the nitrogen cycle bacteria that make terrestrial agriculture possible. It is chemically reactive in ways that would be toxic to plants without treatment. Experiments have shown that plants can grow in regolith-like material with substantial nutrient supplementation and careful management, but can grow under controlled conditions in an experiment is very different from can reliably feed a colony of hundreds or thousands.
Water must be extracted from ice or chemically bound water in minerals, purified and distributed. Power generation at scale likely requires nuclear reactors. Nuclear power is the only technology currently mature enough to provide reliable high-density power independent of sunlight. Those reactors must be launched from Earth, transported to Mars, deployed, maintained, and eventually decommissioned safely. All the medical care that a population requires, from routine illness to surgery to childbirth to mental health treatment, must be available at the colony. A medical emergency requiring evacuation to Earth would involve a minimum 6-month transit. That is not a realistic medical response time for most acute conditions. The manufacturing capability required to produce spare parts for the complex systems that keep a colony alive would itself require extensive infrastructure to establish. Raw materials must be extracted and refined. Fabrication equipment must be operated and maintained. The workforce that does all of this must eat and breathe and receive medical care while doing it. None of this is impossible in principle, but it is decades of sustained, expensive work minimum to achieve. The idea that a few hundred people could land on Mars and build a self-sufficient civilization within a few generations or two is not supported by any serious engineering analysis. It is a multi-generational project requiring continuous investment from Earth.
The Deep Space Challenge. What lies beyond Mars? Mars is the nearest planetary neighbor. The next question is, how much harder does it get from there? Jupiter is 5 times farther from the Sun than Earth. Saturn is 10 times farther. Travel time with current propulsion technology, the Hohmann transfer orbit, the most fuel-efficient trajectory between planets, is roughly 6 years to Jupiter, 7 years to Saturn. Radiation around Jupiter is intense enough that the planet's magnetic field traps charged particles in belts that would deliver lethal radiation doses to unshielded humans within days. Europa, the moon considered most interesting for potential life due to its subsurface ocean, orbits directly through these belts. Any surface or near-surface mission to Europa would require extraordinary radiation shielding. Beyond Saturn, sunlight falls to levels that make solar power essentially impractical. Nuclear power becomes the only viable option. Communication delays with Earth become hours. A crew in the outer solar system is not just isolated from Earth in the psychological sense. They are operationally alone, unable to receive timely guidance, unable to expect any assistance that matters on a timeline measured in years.
The interstellar question: what physics actually allows? Proxima Centauri, the nearest star to our own, is 4.24 light-years away. 1 light-year is approximately 9.5 trillion kilometers. 4.24 light-years is roughly 40 trillion kilometers. Voyager 1, launched in 1977 and currently the most distant human-made object, is traveling at roughly 17 kilometers per second. At that speed, reaching Proxima Centauri would take approximately 73,000 years. To reduce that to a human timescale, say 40 years one way, a full career, you would need to travel at roughly 10% of the speed of light. 10% of light speed is 30,000 kilometers per second. Voyager 1 travels at 17 kilometers per second. The difference is a factor of roughly 1,700. Achieving 10% of light speed with any technology we currently have or are close to developing is not a matter of building bigger rockets. The energy required to accelerate a spacecraft with crew, life support, food, water, and shielding to that speed and then decelerate again at the destination exceeds the total energy production of the entire current human civilization by many orders of magnitude. This is not an engineering challenge that yields to incremental improvement. It requires something qualitatively different from anything in our current technological toolkit. Theoretical proposals exist. nuclear pulse propulsion, essentially detonating small nuclear bombs behind a large pusher plate, could potentially reach a few % of light speed with a large enough craft. Fusion drives, if they could be built, might do better. Antimatter annihilation drives would be the most energy-efficient possible option under known physics, but producing antimatter requires vastly more energy than it contains, and current production rates are measured in nanograms per year. A single interstellar spacecraft would require grams or kilograms of antimatter. What all of this means for how we think about Earth. Here is the underlying point that all of this physics and engineering converges on. Earth is not simply convenient. It is the product of conditions that, as far as we know, are rare in the universe. Liquid water in stable quantities, an atmosphere with the right composition at the right pressure, a temperature range where chemistry can operate at the speed needed for life, a magnetic field that deflects the most damaging radiation, a moon large enough to stabilize Earth's axial tilt, preventing the kind of chaotic climate swings that would make long-term evolution difficult. A giant planet, Jupiter, in an outer orbit that gravitationally deflects many of the asteroids and comets that would otherwise bombard the inner solar system. These conditions took billions of years to develop and billions of years to remain stable enough for complex life to evolve. The probability of finding them all together in the same place is unknown. We do not yet have a good census of Earth-like planets, but the evidence so far suggests it is not common. Human beings are not adapted to the universe in general. We are adapted to one specific planet on the inner edge of the habitable zone around a middle-aged G-type star in a quiet spiral arm of an ordinary galaxy. Remove us from that context and we survive for roughly 2 minutes, less if we are exposed directly to the vacuum. Understanding this is not meant to be discouraging. It is meant to be accurate. The exploration of space is one of the most important things humanity does. It expands our knowledge. It develops technology that benefits life on Earth. It tests human capability in ways that nothing else does. Eventually, it may provide a path to genuine long-term survival as a multiplanetary species. But that path runs through an environment that is actively, profoundly hostile to every biological system we possess. Space does not bend its rules for courage or ambition or the importance of the mission. The vacuum does not care why you are there. The radiation does not make exceptions. The temperature differentials do not negotiate. Every person who has ventured beyond Earth's atmosphere has done so inside a fragile shell of technology, trusting that every seal holds, every pump runs, every calculation was correct. Most of the time, the technology works. Occasionally, it does not, and people die. They died in the Apollo 1 fire. They died when Challenger broke apart on ascent. They died when Columbia disintegrated on re-entry. They died when Soyuz 11 depressurized on descent. Each of those failures was traceable to specific engineering or procedural problems that were corrected afterward. None of them diminished space's fundamental indifference to human survival. The view from here.
Step outside tonight and look up. What you see is not a ceiling. It is not a backdrop. It is a three-dimensional environment extending in every direction for distances that are difficult to hold in your mind. Light years to the nearest star, billions of light years to the visible edge of the observable universe. Nearly all of that volume is vacuum. Nearly all of it is bathed in radiation. Nearly all of it is cold enough that water, the molecule most fundamental to life as we know it, exists only as ice or vapor. The specific cubic kilometer of air you are breathing right now is, as far as we know, extraordinarily unusual.
The human instinct to explore that environment is real and arguably important for our long-term survival as a species. Understanding what is actually out there, not the movie version, not the optimistic shorthand, but the actual physics, makes that instinct more honest. We are not heading into a frontier that is merely challenging. We are heading into a frontier that is fundamentally, structurally incompatible with our biology, and that we can only enter at all by carrying a small piece of Earth with us everywhere we go. That is what makes the astronauts and cosmonauts who have done it remarkable. Not that they were fearless, but that they looked at the actual numbers, understood the actual risks, and went anyway because they decided the value of going outweighed the danger. That calculation deserves to be made clearly with accurate information. And it is what makes Earth worth protecting. Not in the abstract, in the literal sense of this is the only place in the known universe where your body functions without technological assistance. There is nowhere else. Not yet. Maybe someday. But right now, this specific planet, with its specific atmosphere and magnetic field and temperature range and liquid water and oxygen, that is what we have. The universe does not offer a backup. Deep space is beautiful. It is worth exploring. It is worth understanding. And it will kill you in under 2 minutes if you are not protected against it. That is not an opinion. That is physics.